Hi, I'm going to present to you some important formulas and explain solved problems in chapters 1 and 2 of the book Principles of Electronic Communication Systems by Frenzel. Let's start. So the first two parameters are frequency and wavelength. Frequency is the number of times a particular phenomenon occurs in a given period of time. In electronics, frequency is the number of cycles of a repetitive wave that occurs in a given time period. The unit of frequency is Hertz, named for the German physicist Heinrich Hertz, who was the pioneer in the field of electromagnetics. 1 cycle per second is equal to 1 Hertz. Therefore, 440 cycles per second is equal to 440 Hertz. Okay, now let's go to this parameter, wavelength. So wavelength is the distance occupied by one cycle of a wave, and it is usually expressed in meters. Okay, so we have here the Greek letter lambda to represent the wavelength, and it is equal to the speed of light, or letter C, divided by the frequency, since we know that electromagnetic waves travel at the speed of light. Okay, so the speed of light is actually 299,792,800 meters per second, or approximately, this is 300 million, or 3 times 10 raised to 8 meters per second. So we have here the figure illustrating the distance of one cycle of a wave, which is the wavelength. Okay, now let's review some of these in the electromagnetic spectrum. Okay, so this is the electromagnetic spectrum for electronic communication. So let's have this first one. Okay, so here we have the important, this is the commonly used or the most frequently used prefixes. Okay, so we have K to represent the kilo. Kilo means 1,000, 10 raised to 3. And M is for mega. This is 1 million or 10 raised to 6. And G is for giga or 1 billion or 10 raised to 9. And we have T, big letter T to represent tera or 1 trillion or 10 raised to 12. Okay, so the units of measure and abbreviations again. So when we say 1,000 hertz, you can also write it in kilohertz or 1 kilohertz. Okay, and for 1 megahertz, this is equivalent to 1,000 kilohertz, or 1 times 10 raised to 6, basically 1 million hertz. For gigahertz, this is equal to 1,000 megahertz, or 1 times 10 raised to 6, okay, or equal to 1 million kilohertz, okay? Or basically, 1 gigahertz is equal to 1 times 10 raised to 9, or 1 billion hertz. Okay, so again, the letter M here in the electromagnetic spectrum, or the table, the electromagnetic spectrum means meter. And mu M is micrometer, or this is equal to 1 times 10 raised to minus 6 meters. So as you can see, the wavelengths here becomes shorter as the frequency increases, okay? If you recall the formula in the previous page, okay, the wavelength is equal to the speed of light over the frequency. So it means that when the wavelength increases, or when the wavelength becomes longer, the frequency becomes or decreases. Okay, when the frequency increases, the wavelength becomes narrow or becomes shorter. Now let's solve some problems. Okay, let me explain the first problem. Find the wavelengths of, so we're given the following frequencies: 150 megahertz, 430 megahertz, 8 megahertz, and 750 kilohertz signal. So take note that we have different prefixes here. Mega means 1 million, and kilohertz means, or kilo means 1,000. Now, recall that the formula for finding the wavelength is equal to the speed of light, okay, which is equal to 300 million, or 3 times 10 raised to 8. So the number of zeros represent in the scientific notation, we have 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8. We can say 3 times 10 raised to 8. Okay, speed of light divided by the frequency. So first we have the frequency 150 megahertz. So 300 mega divided by 150 mega. Okay, or you can write in this format since you can cancel megahertz. Okay, so 300 divided by 150 is 2 meters. Okay, take note the unit is in meters since we utilized the equivalent speed of light in meters per second. And you know that the unit of frequency megahertz means cycles per second. Okay, now the next one is finding for the wavelength of this given frequency 430 megahertz again. So we just shown here the shorthand method, or I mean the shorthand representation of the speed of light. So you know that the units here are in mega, okay, or times 10 raised to 6. So 300 divided by 430 is equal to 0.697 meters. So as you can see, as the frequency increases, the value of the wavelength becomes shorter. Okay, compared to this one, it's 2 meters given frequency equal to 150, and this is 430 megahertz. So it's bigger than this frequency. That's why the wavelength here is shorter. So the same formula for letter C and letter D in finding for the wavelength. So 300 million meters per second divided by 8 million. So we have 37.5 meters. And so this frequency is smaller compared to the first two frequencies. That's why the wavelength here is longer compared to the first two wavelengths. Okay, so here we have shown you two ways how to write the solution. 750 kilohertz expressed in hertz, or this is 750,000. And the next one is in terms of megahertz. If you want to utilize the unit megahertz, you need to express 750 kilohertz in megahertz. So this is equivalent to 0.75 megahertz. Okay, that's why in the formula here, in the equation here, we have 300 in megahertz divided by 0.75 in megahertz. So you cancel the megahertz units. So 300 divided by 0.75, you have 400 meters. So if you want to express the units of frequencies in terms of hertz, we have 300 million hertz divided by 750,000 hertz. Okay, so that's example number 1. Now we have example number 1-2. A signal with a wavelength of 1.5 meters has a frequency of, okay, so we are given with a wavelength and we are asked to solve for the frequency. So remember, let me just get a pen. Remember that a wavelength is equal to the speed of light divided by the frequency. So now if you are asked to solve for the frequency, just cross multiply. So frequency is equal to the speed of light divided by the wavelength. Now the unit will become hertz. Okay, so since we are going to use this representation, it means that 300, the unit of this is, or the prefix that we are to use is mega, or times 10 raised to 6 here. That's why, so 300 times 10 raised to 6 divided by 1.5, so we have 200 megahertz, okay, as the value of the frequency for a wavelength 1.5 meters. Okay, now let's go to the next page. Example 1-3. A signal travels a distance of 75 feet in the time it takes to complete one cycle. So what is its frequency? Okay, so we can use a conversion here since um, the given distance is in feet. So recall the conversion, 1 meter is equal to 3.28 feet. So since we are going to use the speed of light in meters per second, so we need to convert the given distance from feet to meters. So 75 feet times 1 meter divided by 3.28 feet. So we cancel the feet, the unit feet. So we now have 22.86 meters. And now recall the formula for finding the frequency. It's the speed of light divided by the wavelength. Okay, so again, so this means 300 million, okay, or 300 times 10 raised to 6. So that's why you have here a unit in megahertz. So 300 divided by 22.86. Yeah, shorthand way of writing. So we have 13.12 megahertz. Okay, so now let's go to example number 4. The maximum peaks of an electromagnetic wave are separated by a distance of 8 inches. What is the frequency in megahertz and in gigahertz? So we are to express the frequency in megahertz and in gigahertz unit. Now, we know that 1 meter is equal to 39.37 inches. Then we need to convert this 8 inches distance to meters. So 8 inches times 1 meter divided by 39.37 inches. We can cancel the inches unit. Now the value of the distance in meter is 0.203 meters. Okay, so if you're going to determine now the frequency, so in terms of megahertz, so we will use this value, 300 times 10 raised to 6, or in mega value, divided by the distance, 0.203 in meters. We have 1,477.8 megahertz. Okay, now if we are to express this one, or this frequency in terms of gigahertz, we just move the decimal point to the left 3 times. So 1, 2, 3, and we have now 1.4778 gigahertz, or this is 1.477. Let me just get a pen here. Okay, because this means that this is 1477.8. So in terms of hertz value, 10 raised to 6. And you know that this is mega. So for giga, we have 1.4778 times 10 raised to, since you move the decimal point 3 times to the left, so you have 10 raised to 9. So that is the meaning of this prefix giga, okay? 1.4778 gigahertz. Okay, so let's now go to the next page. Let me just erase this one. Okay, now the next important formula that we are going to learn is the bandwidth. So bandwidth is that portion of the electromagnetic spectrum occupied by a signal. It is also the frequency range over which the receiver or other electronic circuit operates. Again, bandwidth is the difference between the upper frequency and lower frequency limits of the signal. Okay, so this is the formula. Bandwidth is equal to f sub 2, or the upper frequency, minus f sub 1, or the lower frequency. Now let's have this problem. A commonly used frequency range is 902 to 928 megahertz. What is the width of this band? So width means the bandwidth, since we are given the range of frequency. Now, the lower frequency is 902 megahertz, and the upper frequency is 928 megahertz. To determine the bandwidth, you have to take the difference, or You subtract 902 from 928, so we have 26 megahertz as the bandwidth for this range of frequency. Okay, the next problem here, a television signal occupies a 6 megahertz bandwidth. If the low frequency limit of channel 2 is 54 megahertz, what is the upper frequency limit? Okay, so we have the bandwidth equal to 6 megahertz. I think we need to correct this one. So this should be, so the 6 megahertz here is the bandwidth. Okay, just correct this. And it says that the lower frequency limit, so this should be f sub 1. Okay, now we are asked to solve for the upper frequency, or f sub 2. You transpose this to the left-hand side and transpose bandwidth to here. Yeah, so we have, okay, I think the formula is, it should be f sub 2 minus f sub 1. So let me just get my pen. Okay. Okay. Okay, so this should be, okay, let me just correct this one. Let's go back to the previous slide. Okay, this should be f sub 2 minus f sub 1. So you transpose f sub 1 to the left-hand side, it will become bandwidth plus. There's a typo, graphical error here. Okay, let me just rewrite this one. So again, remember that bandwidth is equal to f sub 2, or the upper frequency limit, minus f sub 1. Okay, so we are given with the lower frequency limit. Now we are asked to solve for f sub 2. So f sub 2 is equal to, okay, we have now this formula. Okay, so disregard this one. So we have the upper frequency limit equal to the bandwidth plus the lower frequency limit. So 6 plus 54, we have 60 megahertz. So that is the upper frequency limit. Okay, now let's proceed to the next page. The next parameter here is the gain. Okay, gain for most amplifiers. Okay, gain means amplification. Okay, so we have here the input signal, or V sub V in, and V out is the output signal. So V in terms of voltage. So gain is a unitless parameter. So this is the ratio of the output signal over the input signal. Again, this is a unitless parameter. Now let's solve this one. What is the voltage gain of an amplifier that produces an output of 750 millivolts for a 30 microvolts input? Okay, so again, the voltage gain or gain of an amplifier can be determined by taking the ratio of the output voltage or output signal over the input signal. Now, okay, sorry for that. So the output signal here is 750 millivolts, or 750 times 10 raised to minus 3 volts. Okay, need to express your answers in terms of volts. So you need to write here in the scientific notation. Now, for the input, we have 30 microvolts. So 30 times 10 raised to minus 6 volts is equal to 30 microvolts. Now, using a calculator, so we can determine the gain, which is equal to 25,000. Again, this is a unitless parameter. So, or amplification. So the amplification, parameter. The next problem is finding for the power out, finding for the input power. So it says that the power output of an amplifier is 6 watts, represented by this letter as a unit of power. The power gain is 80. So here, you're given the gain and the output. What is the input power? So even though in the previous slide, the gain is equal to the output voltage over the input voltage. So that's actually voltage gain. So now we're talking about the power outputs. So the involved ratio here are the powers. So power output over the power input is the power gain. Since we are given with the power output and the power gain, we can now determine by cross multiplying this one, interchanging their or I mean, not the positions, but cross multiplying. So we have the input power equal to the power output over the power gain. So logging in the values into this formula, we have 6 watts divided by 80. So we have 0.075 watts, or if you are to express this value in terms or using the prefix, so this is equal to 75 milliwatts. Next example, 3 cascaded amplifiers have power gains of 5, 2, and 17. The input power is 40 milliwatts. What is the output power? Now the output power is equal to the product of the 3 gains or cascaded power gains. Okay, so power gain number 1 of the first amplifier multiplied to the power gain of the second amplifier times the power gain of the third amplifier. So again, you can only do this for a unitless power gains. Okay, so 5 times 2 times 17 is equal to 170. Since we are asked to solve for the output power, now we have the value of the power gains in a cascaded configuration. So power gain is equal to output over input. Therefore, to solve for the power output, multiply the power input by the power gain. So here is the formula. So we have 170 times 40 milliwatts, or 40 times 10 raised to minus 3 watts. Therefore, the value of the power output is 6.8 watts. So it should be greater than the power input since it amplifies. Again, gain means amplification. Okay. Now we have this example. A two-stage amplifier has an input power of 25 microwatts and an output power of 1.5 milliwatts. One stage has a gain of 3. What is the gain of the second stage? So recall the formula for the power gain. It's power output over the power input. Now, the power output is equal to 1.5 milliwatts. That's 1.5 times 10 raised to minus 3 divided by the power input, which is 25 microwatts, or 25 times 10 raised to minus 6. So the power gain is 60. Now we are asked to solve for the gain of the second stage. Now, how do we do that? We are given what the gain of the first stage. So since this is the total or power gain of the two-stage cascaded amplifier, so remember that to find the gain or power gain of a two-stage amplifier, we have to multiply their gains, right? So we use this formula, so we are given with 60, and we are given also with the first stage gain. So we divide the power gain by the first stage gain. So this is now the result. So 60 divided by 3 is the gain of the second stage, which is equal to 20. Okay, the next parameter is the attenuation. So if we have the gain, we now have the attenuation. Attenuation refers to a loss introduced by a circuit or component. If the output signal is lower in amplitude than the input, circuit has a loss. Okay, remember this. If the output signal is lower in amplitude than the input, it has a loss or attenuation. So like gain, attenuation is simply the ratio of the output to the input. So the same formula with that in a gain. The difference is again that in gain, the output is greater than the input. In attenuation, the output is lower than or less than the input. That's why there's a loss or attenuation. Okay, I have here an illustration showing you the voltage divider. Okay, I think there's a two network here, an amplifier, and this circuit here is the first stage of this cascaded network. So this is a voltage divider. Now to determine the gain here, so let me just get a pen here. Okay, so we know that the gain is equal to the output, okay, output voltage over the input voltage. Okay, so, and in this network, we are given the gain of the second stage. So we need to know the gain of the first stage. So how do we do that? It says here, there's a condition that the output is equal to the input. That's why we're going to use a voltage divider here to solve for this one. So 250, that is actually, okay, so if you are to solve for the output voltage, which is the voltage across this resistor, and that is, let's label these resistances. So if this is R1 and this is R2, okay, so the output is measured here, connected to this amplifier. So the voltage divider, we have the input voltage, yeah, V in over V in times the resistance R2 over the total resistance, or basically you just add them. So R1 plus R2. Okay, so again, remember the condition here, V out is equal to V in. If we are to plug in here, so V out is equal to V in, okay, times this ratio, okay, R2 over R1 plus R2, and then divided by the input. Okay, we can cancel this one. Okay, so I think that's it. So now the gain for the first stage can be determined by, of course, these values of the resistances. So that's why we have 250 divided by the sum, the total resistance. Okay, 750 plus 250 is actually equal to the gain of the first stage of this network. So we have now 0.25, and then connected to another amplifier cascaded. So ibig sabihin, yung output dito is connected, is the input to this amplifier. So the total gain is just the product of the two, of the first stage gain and the second stage gain. So this is equal to 1. Okay, so now let's go to the next page. So recall this circuit, because we are going to use that in this example. A voltage divider, as shown in the previous figure, has a value, has an R1 equal to 10 kilo ohms and R2 equal to 470 ohms. So what is the attenuation? And let it be, what amplifier gain would you need to offset the loss for an overall gain of 1? So for the first item here, to solve for the attenuation, so we just need to use the ratio or this formula for voltage divider. So R2 over R1 plus R2, so that's 470 divided by 10,000 plus 470 are equal to 10,470. So therefore, we have the attenuation equal to 0.045. Now, what amplifier gain should you need to offset the loss for an overall gain of 1? Remember, the total gain, if there are two stage or two amplifiers in cascade, so the gains are being multiplied. Unitless gain are multiplied. Remember that A sub 1 is attenuation and A sub 2 is the amplifier gain. So what is that gain to offset the loss? Okay, and you are given the overall gain equal to 1. So attenuation multiplied by the gain to offset the overall gain 1. Thus, we have A sub 2 equal to 1 divided by 0.045, which is equal to 22.3. Now, if you multiply 22.3 to the first stage gain, will give us the overall gain equal to 1. Okay, so to find the gain that will offset the loss for unity gain, just take the reciprocal of attenuation. So this is just, another reminder. So just the reciprocal, just like this. 1 over A sub 1 is the gain to offset, okay, the loss for unity gain. So let's now take a look at this illustration here. We have total gain is the product of the individual stage gains and attenuation. So remember that total gain is just the product. So, and these gains are unitless. Okay, so A sub 1 is the first stage gain. This is the loss stage. A sub 2 is equal to 10. Again, remember, if the value of the gain is less than 1, it's actually an attenuation or a loss. If it's greater than 1, it is a gain. And this one is a loss or attenuation since it's less than 1. And this is the value of a gain. Now, to determine the total gain, just have to multiply these gains and attenuations. Let's solve this. An amplifier has a gain of 45,000, which is too much for the amplification. With an input voltage of 20 microvolts, what attenuation factor is needed to keep the output voltage from exceeding 100 millivolts? So let A sub 1 equal to amplifier gain, which is 45,000, and A sub 2 is the attenuation factor, okay, or the loss, and A sub t is the total gain. Now, so the total gain, remember, gain is equal to the ratio of the output over the input. We just have to solve this. So 100 millivolts is the output voltage divided by the input, which is 20 microvolts or 20 times 10 raised to minus 6. Now we have the total gain, 5,000. Now to solve for the attenuation factor, or A sub 2, so recall the formula, and that is if we have two amplifiers or two stages in cascade, so you need to multiply them. So A sub 1 amplifier gain times attenuation factor. Therefore, to solve for the attenuation factor, you need to divide the total gain by the first stage amplifier gain. So 5,000 divided by 45,000 is equal to 0.111. So it's just, what we're expecting because it's attenuation, so it should be less than 1. Now the next parameter is the decibels. So the gain or loss of a circuit is usually expressed in dB or decibels. This is a unit of measurement that was created as a way of expressing the hearing response of the human ear to various sound levels. So decibel or deci is 1/10 of a bell, okay, decibel. So these are the formulas for computing a decibel gain or loss of a circuit. So previously we have a gain that has no unit. So here to express, okay, the gain or loss in dB. These are the formulas. If you're given with a voltage, so V out over V in is the unitless gain. So to make this a dB value, so take the logarithmic of the ratio of the gain times 20. This is the dB gain in terms of voltage. Now for the given current, our current gain in dB, so you need to take the ratio of the output current over the input current and take the log or the logarithmic of this ratio times 20, and that is the dB value of the current gain. Now, if we're given the power, so power output over power input, take the log of this ratio and multiply it by 10, and you will have the dB value of the power gain. Okay, for example, an amplifier has an input of 3 millivolts and an output of 5 volts. What is the gain in decibels? Okay, again, so we are asked to find for the gain in decibels. So the formula, since we are given with input voltage and output voltage, so it's 20 log of V out over V in. So V out is 5 volts, and you express this input into volts, so it's 0.003 or 3 times 10 raised to minus 3 volts. So log of this ratio times 20 is equal to the dB gain, or the gain in decibels, 64.4 decibels. So just write dB. So a filter has a power input of 50 milliwatts and an output of 2 milliwatts. What is the gain or attenuation? So we don't know. If it's a gain, it should be positive. If it's attenuation, it should be negative. Now, so the given is power input and power output. Okay, so power output over power input is the power gain. To express it in dB, so you need to take the log of the ratio of the power gain times 10. So that's the dB value. So 2 milliwatts divided by 50 milliwatts. So you need not to convert this, since both are in milliwatts units. So 2 divided by 50, and then take the log of this times 10 is equal to negative 13.98. Take note that if you are taking the log of a number less than 1, it will become negative. Okay, if you're taking the log of a number greater than 1, the answer is positive, just like this. Okay, so what can you say about the answer here? Since it's negative, it is an attenuation. Okay, so again, we have a reminder here. When the circuit has gain, the decibel figure is positive. Okay, just like what I've said earlier. If the gain is less than 1, which means that there's an attenuation, the decibel figure is negative. Okay, so less than 1, if you take the log, it's negative. If it's greater than 1, the value is positive, so it's a gain, and this is an attenuation. Okay, so take a look at this one. Total gain or attenuation is the algebraic sum of the individual stage gains in decibels. So take note, we take the sum for the dB values of the gain, so we do not multiply them. So for the unitless gains, you multiply them, but when we're talking about the dB values of the gain, we are to add or subtract them depending on the sign, if it's a loss or if it's a gain. Just like this, we have a 3-stage network here, or illustration. So the first stage gain is 15 dB. The second stage has a loss of minus 20 dB. And the third stage is a gain equal to 35 dB. So if you are to determine the total gain or attenuation, so you just have to add them. So 15 minus 20 plus 35, so you have a positive value, 30 dB. So it means the total gain is 30 dB. If it resulted to minus, it means that you have a total attenuation. Now for the antilogs, to calculate the input or output voltage of power given the decibel gain or attenuation and the output or input, the anti-log is used. The anti-log is the number obtained when the base is raised to the logarithm, which is the exponent. So just like this, if you are asked to solve for the power gain, so the dB value is equal to 10 log of the ratio of the output over the input. So just divide both sides by 10, and then to eliminate the log, so take the anti-log of both sides of the equation. So you have yeah, 10 raised to this log equal to, we'll be able to eliminate this one. So anti-log of, or 10 raised to dB over 10. Okay, 10 raised to dB over 10. That's it. That's the anti-log. Yeah, for example, a power amplifier with a 40 dB gain has an output power of 100 watts. What is the input power? Okay, we are asked to solve for the input power, and now we are given with the power gain 40 dB and an output power 100 watts. So we call it the formula for the power gain in dB is 10 log of the power output over the power input. Now, so we get the anti-log here. We are to solve for the power input. So anti-log of, divide both sides first by 10, and then take the anti-log. So we have 10 raised to, the dB value is 40, right? So 10 raised to 40 over 10, and then we have P out over P in. Okay, this is now the part where you take the anti-log. So now we have, yeah, just like this. So anti-log of 4 is equal to 10 raised to 4. Now to solve for the input, so cross multiply. So power output, which is 100 watts, divided by the equivalent on the right-hand side of the power gain, which is 10,000. Now you have the power input equal to 0.01 watts, or if you were to express that in terms of the prefix milli, so 10 milliwatts is the answer. Okay, next example, an amplifier has a gain of 60 dB or decibels. If the input voltage is 50 microvolts, what is the output voltage? Now we are given with a voltage value, so it means that the gain here is the voltage gain. So the formula is 20 log of the ratio of the output over the input. Okay, remember it's voltage, so 20 yung ginamit. Now, divide both sides by 20 and then take the anti-logs. So we have 10 raised to, what is the dB value? So 60 divided by 20, that is 3. That's why if you are to take the anti-log, so it's 10 raised to 3. 10 raised to 3 equal to 1,000, right? So given tayo ng input voltage, you're asked for the output. So V out is now equal to 1,000 times the input voltage, which is 50 microvolts, or 50 times 10 raised to minus 6. So you have the output equal to 0.05 volts, or expressed in the prefix milli, so 50 millivolts. Now the next example here, a power amplifier has an input of 90 millivolts across 10 kilo ohms. The output is 7.8 volts across the 8 ohm speaker. What is the power gain in decibels? You must compute the input and the output power levels first. All right, so recall the formula for the power in terms of the voltage and resistance. So power is equal to V squared over R using Ohm's law. So to solve for the power, you have the given input, which is 90. So 90 times 10 raised to minus 3. You square that voltage, input voltage, and then divide that by the resistance equal to, the resistance here is 10 kilo ohms for this particular input. So 10,000. Okay. So this is 10,000, so supposedly. So we have, okay, let me check my calculator. Yeah, 10,000 is right. 4 zeros. So the value of the input here is 8.1 times 10 raised to minus 7 watts. Okay, now we are to solve for the power output. So the involved voltage here in the output is 7.8 volts, and the resistance is 8 ohms for the speaker. So 7.8 squared divided by 8 is 7.605 watts. Now to solve for the gain, and that is equal to the ratio of the power output over the power input. So we can now determine the unitless gain, 7.605 divided by the input power, 8.1 times 10 raised to minus 7. So the value of the power gain, unitless power gain, is 9.39 times 10 raised to minus 6. Okay, or this is 9,390,000. Okay, so then we take the log, since we are asked to express the power gain in decibels. So 10 log of the power gain is equal to the dB value. So 10 log of 9.39 times 10 raised to 6 is equal to 69.7 decibels. Okay, so let's take a look at this one. So the dBm and the dBc unit. So when a decibel value is computed by comparing a power value to 1 milliwatt, the result is a value called the dBm. It is computed with a standard power decibel formula with 1 milliwatt as the denominator of the ratio. So power output over the 1 milliwatt reference or the denominator. So you have the dBm unit for whatever it is that you're solving, attenuation or gain. For dBc, okay, this is a decibel gain attenuation figure where the reference is the carrier. The carrier is the base communication signal, a sine wave that is modulated. So often the amplitude sidebands, spurious or interfering signals are referenced to the carrier. Again, reference is the carrier. For example, if the spurious signal is 1 milliwatts compared to the 10-watt carrier, the dBc is, so this is just how you, this shows how you compute the dBc value, 10 log of the signal power divided by the reference, which is the carrier. So you have a spurious signal, 1 milliwatt divided by the carrier, which is 10 watts. So this is the result. Okay, log of this ratio times 10 is the dBc value. Okay, let's have more examples. An amplifier has a power gain of 28 dB. The input power is 36 milliwatts. What is the output power? So recall that the ratio of the power output over the power input is, of course, the unitless gain. So to determine this ratio, unitless ratio, so we get the anti-log. So 10 raised to the dB value 28 divided by 10, which is, of course, that 10 log in the formula. So let me just write so that you can be able to see what I meant about. So the dB gain is, power gain is equal to 10 log of the ratio of the power output over the power input. Okay, so we have here 10 dB divided by 10 and then get the anti-log. So it's 10 raised to 0.28. So this is the value. And if you determine the output power, just have to multiply this unitless gain to the input power. So you now have 22.71 watts. Okay, so let's now go to the next example. A circuit consists of two amplifiers with gains of 6.8 and 14.3 decibels and two filters with attenuations of minus 16.4 and minus 2.9 decibels. If the output voltage is 800 millivolts, what is the input voltage? So total gain in dB value, so you just have to add them. So A sub 1 plus A sub 2 plus A sub 3 plus A sub 4. Again, this is in dB value. So you have 6.8 for the first two amplifiers, so 14.3. The next filter is attenuation, so minus yan, so minus 16.4 and minus 2.9. So you have a positive value, ibig sabihin may gain ka, 1.8 decibels. Now we are asked to solve for the input voltage. Now you know that we need to determine the unitless gain. Okay, so we need to express this into a unitless gain. So recall the formula, 20 log, right? So let me just, again, get my pen here. Recall the dB value for the voltage. That's 20 log of the ratio of the output over the input. Okay, so we are asked to solve for what? The input. So we need to get the unitless value, okay, of this 1.8. So dB value, so 1.8 divided by 20, and then equal to log of the ratio, so V out over V in. So to eliminate the log, so you need to take the anti-log, so 10 raised to this exponent. Both sides of the equations, you can be able to cancel this. So you now have this value for the unitless gain, and that is 1.23. So to determine the input voltage, given that you have the output voltage 800 millivolts, or 800 times 10 raised to minus 3. So we have this result, 800 millivolts divided by 1.23 as a unitless gain, equal to 650.4 millivolts. Okay, so that's it. Now let's see if we still have another problem here. Okay, express output power equal to 12.3 dBm in watts. So again, it's in dBm unit. So dBm means that the reference is 1 milliwatt. Okay, 1 milli. So what did we do here? We divide both sides by the reference point 0.001. Okay, so how did we do this? Power output over the input. Input is the reference na 1 milliwatt. Okay, anti-log lang to. So you have now the gain of this dBm value. So, okay, let me just write so that you can be able to see what I meant here. Remember that the dBm unit is equal to, okay, we're talking about the power, so it's 10 log of the output power over the reference, which is 1 milli, okay, or 1 times 10 raised to minus 3, or you can express this in terms of decimals, so it's 0.001. Now to eliminate the log, divide both sides by 10, so you have dBm over 10, and cancel this one, and then take the anti-log, so 10 log of this exponent, okay, and 10 log of this on the other side. So you have 10, the dB value is 12.3 divided by 10, ito yun. So the answer is 17. And to solve for the power output, so just have to multiply 0.001 by 17. So you have the power output equal to 17 milliwatts. Okay, so I think that's the end of this presentation. So we were able to solve or to show you the solutions to problems in chapters 1 and 2 of the subject Fundamentals of Electronic Communication.